Welcome to the VLSI technology lecture. So today in this lecture, we are going to see how different dielectrics and polysilicon layer can be grown over the, it can be deposited over the wafer, okay, after fabricating the circuit or during the fabrication of the any device, we need to deposit these layers at various stages. So that we have to see today, okay, in this particular lecture, how these different dielectrics and polysilicon layers can be deposited. So first of all, you try to see this picture, okay, in which we can see generally we have the two different dielectrics, okay. One is our SiO2 and second one is our silicon nitride, okay. So that two layers we generally deposit during our device fabrication. Another layer that we generally grow is our polysilicon, so that we can understand from this picture, okay. So here you can see this in this particular picture. We have this source region and here we have this our drain region, okay. And here you can find that between the source and drain, we generally have a particular gate terminal, okay. And in between, we normally having a very thin oxide. So here you can see we have grown one oxide layer, a very thin oxide layer. And then here you can see we have another SiO2 layer whose thickness is very high, okay. So here we have this polysilicon gate. Then you can see here you can find another SiO2 layer that we have, okay. And here you can see this is our polysilicon layer, okay, which is making a contact with this particular N plus source. And again, here you can see another SiO2 layer that we have grown over here, okay. And here again, we have this polysilicon layer, okay. So here you can see after this polysilicon layer, again, we have deposited this aluminum and then we have made the contact to the outside void. Again, you can see after having this aluminum coating, okay, we also have grown here. You can see a dielectric silicon nitride, okay, for its passivation of this particular device, okay, for its final passivation. So here you can see we have different SiO2 layer of different thickness. One is known as like gate oxide, okay, generally it is thermally grown, so it is gate oxide. And wherever we don't require any device, that places we generally grow a very thick oxide layer, SiO2 layer, which is normally referred as the filled oxide, okay. So generally we have the SiO2 layer, you can see, and then we can have the polysilicon layer that we have deposited here. And we can also have, we can see that we also have the metallization, okay. This is generally means our aluminum layer, okay, that we have deposited here to make the contact, okay. And again, we have the silicon nitride. So these are the different layers that you can see from this particular picture. So here again, if you recall this picture I had used while discussing the silicon on insulator device. So in that case, when I was discussing about the shallow trench isolation, okay, that time you might be remembering that we had used this particular silicon nitride layer at this particular place, okay. So basically we are using somewhere we are using the silicon nitride, sometimes we are using silicon dioxide, okay. We are using the polysilicons, we are using aluminum, okay. So all these different layers are having their different functionalities, okay. So we have to understand what are the different functionality of these layers and how these layers actually we are depositing, okay. So that we have to understand. So here you can see this filled oxide is generally used for isolating the two adjacently placed devices, okay. So wherever you find this thick oxide layer, it is generally used as a filled oxide. It is referred as the filled oxide and it is used for isolating the two adjacently placed devices. So let's try to understand and that what are the uses, okay, of this particular layers. Then we will be subsequently see how this layer can be deposited. Okay, how these layers can be deposited. So that we will be seeing in the subsequent sections. So now first you try to see, as you can see, SiO2 layer is actually acting like a, means here it is acting like a gate oxide, somewhere it is acting like a field oxide. Okay, so basically it is obviously it is an insulator. Okay, so it is having the insulating property. So that we generally used for the insulation. Okay, and it is also used for the isolation between the two devices. Here you can see that this silicon nitride, which is again a dielectric, it is used generally for the passivation of your final device. Okay, we also use SiO2 layer for the final passivation, but sometimes we also use the dielectric as a SiN for our final passivation. Okay, so that the layers which is under this dielectric layer will not be contaminated, and it can be protected from the external environment. So that's why we are using this dielectric. Okay, similarly you can see this polysilicon is having metallic property, and therefore it is used for making the connections. It is also used for making the gate electrode. Okay, and obviously aluminums are used for making the connections. It can be used for like a metallic wires. Okay, metallic connections at different levels of the devices can be used, and it will be also used for making the final electrode or pin, you can say. Okay, so the terminal that we generally take out from the device is generally made up of aluminum. Okay, so here you can see in this slide, okay, that we generally have these type of layers that we want to deposit onto our devices. Okay, here you can see polysilicon, silicon dioxide. Then we have the two categories of silicon nitride. Okay, the first one is known as the stoichiometric silicon nitride. Okay, whose chemical formula is Si3N4. And then we have the plasma deposited silicon nitride, whose chemical formula, it can either be represented as SiN or SiNH. Okay, generally it contains 20 to 25% hydrogen. Okay, and it is having low density as compared to your stoichiometric silicon nitride. So these are the two different nitrides that we have. Okay, and last one is our metals films that we can deposit. Right. So here you can see its typical uses. Okay, what is polysilicon does? Okay, what is its functionality? Okay, what the silicon dioxide does? Okay, so here you can see it is acting as a gate electrode material in MOS devices. It is a conducting material for multi-level metallization process. Okay, contact material. Okay, it is a contact material for devices with shallow junctions. Okay, and then the silicon dioxide, as I said, that in the silicon dioxide, generally it can be of undoped SiO2 or it can be a doped SiO2. Okay, so to change its property, we can sometimes we also dope it. Okay, so undoped SiO2 is actually, as I said, it is an insulator. So it will be acting as an insulating layer between multi-level metallization. It is, you must be remembering that we use the SiO2 layer as a diffusion and ion implantation mask. Then it is also used as the capping layer over the doped films to prevent the loss of dopants. So what does it mean by the capping layer? So let's suppose that you have already done the diffusion. Okay, you have already done the diffusion. Some of the dopants are already doped at a particular region, and after that, if you want to perform any high temperature process, generally what happens is, because of the high temperature, there is a chances that this doped region, the dopants within the doped region may come out, and it may also go to some other places. Okay, it may also go to the other places. Okay, so if you want to prevent that, because you don't want that this dopants go from this particular place to somewhere else. Okay, you don't want it. Okay, so that time we have to develop a capping layer. Okay, just deposit one SiO2 layer, and you knowing that SiO2 layer is having a good, means the diffusivity of this your dopant materials is very small, and therefore it cannot migrate from its places. Okay, it will be remain there even if you are performing any high temperature operation. So this is what the capping layer means. So basically these are the uses. Okay, then the phosphorus doped SiO2 layer that we are using is one of the properties, the gettering source of impurities. I have already explained what is the gettering means. Okay, so it is also acting as a gettering source for impurities, right? Obviously it is used for the passivation. Okay, it is a passivation layer to protect the devices from impurities, moistures, and scratches. Okay. You see one more typical uses of SiO2 layer is the oxides, which is doped with the phosphorus, arsenic, or boron. Sometimes it is used as a diffusion source. Okay, if you want to diffuse the phosphorus, arsenic, or boron, okay, sometimes we use this SiO2 doped with this dopant as a source. Okay. Now here you can see this stoichiometric silicon nitride are generally used to passivate the devices. Okay, as they serve as the good barriers to the diffusion of water and sodium. Okay, so that's why it is used as the passivating layer. Okay, so generally the water and sodium cannot penetrate through this silicon nitride layer, Si3N4. Okay, it is not only Si3N4, this SiN, okay, which is your plasma deposited silicon nitride. Both are possessing this property. It is having a very excellent barrier. It is acting as an excellent barrier to the diffusion of the water molecules and the sodiums. You remember that water molecules and sodiums, if it penetrates through, and if these impurities enters into the device, it will start corroding your device. Okay, so that's why these impurities are very dangerous to your devices. Okay, and that's why we generally use this Si3N4, okay, or SiN for to passivate our device. Means at the final stage, we using this particular layer passivate our devices. Okay. You see when we have the dual dielectric device. Okay, if we need to have the dual dielectric device, that time this silicon nitride, stoichiometric silicon nitride are also used. Okay. Basically, as a gate dielectric, we can use the SiO2 layer, means thin oxide layer, okay, thin SiO2 layer, or we can also use the Si3N4, okay, if we want to use the two different oxide. Okay, so in the dual dielectric devices, we generally use this stoichiometric silicon nitride. Okay. Here we have the plasma deposited silicon nitride. Okay, so when I will be discussing about the plasma deposited silicon nitride, how it is deposited, okay, that time you come to know that generally this process can be done at low temperature. Okay, generally this stoichiometric silicon nitride deposition is done at higher temperature. Okay, so for the final passivation, because you know we had already deposited like aluminum. Okay, so when we had already deposited aluminum, then high temperature process cannot be done at the last stage, because the aluminum's melting point is somewhere around 650 degree or 700 degree. Okay, so if we perform a very high temperature operation at the last stage, then this silicon will melt down, your aluminum will melt down. Okay, so normally we deposit the plasma deposited silicon nitride, which is a low temperature process. You remember, if you have not deposited aluminum, if you just having the polysilicon layer, then over the polysilicon layer you can means grow this stoichiometric silicon nitride layer also. Why? Because the melting temperature for your polysilicon is very high. Okay, it is around 1400 degrees centigrade. So we have to think about what are the layers that we have already grown, and then finally we have to decide whether it should be a low temperature operation or it should be a high temperature operation, so that the underneath layer should be intact. Okay, it should not be going to affect your already deposited layers. Okay. So you remember that the aluminum is having lower melting point than your polysilicon. Okay. So this is what are the uses of this different materials. Obviously, the metal film like aluminum or silicides. Okay. This will be used to make the low resistance interconnections. Okay, or make contacts and rectifying metal semiconductor barriers. So as your name suggests, we have to go for the deposition process. Okay, so generally it is done in the chemical vapor deposition. Okay, we have to go for the CVD technique of a chemical vapor deposition, in which there will be a certain chemical reaction that is going to take place, and due to this chemical reaction, the product which is going to form is our desired layer. Okay. So here you can see we have the, like I already explained you about, we have the atmospheric pressure CVD, okay? We have the low pressure CVD. We also have the plasma enhanced CVD, okay? So these are the different chemical vapor deposition chambers or reactors, you can say, that we can use generally for deposition of these layers. Normally, we don't use the atmospheric pressure CVD, okay? We don't use. One of the reason is that when we grow the layers using the atmospheric pressure CVD, the grown layer or the deposited layer is having a non-uniform thickness, okay? And therefore, generally, we don't go for the APCVD technique, okay? So here you can see the details of the low pressure CVD technique and plasma enhanced CVD technique. Okay, so this is our hot wall reduced pressure CVD technique. Okay, here you can find that we have the quartz tube, and then again we have the 3-zone furnace. Okay, so these wafers will be placed, and then the gas will be passed from one side. Okay, the mixture of the gases from this gas inlet, and it will be passed through this particular chamber. It will be heated up to a particular temperature. So generally in the hot wall reduced pressure or low pressure CVD reactors, generally the temperature that we use is around 300 to 900 degrees centigrade. It will be depending on what layer we want to deposit. Okay, so this is the typical variation of the temperature that generally this particular system is having. Okay, the pressure that will varies from 32 to 50 pascals. Similarly, the typical gas flow that we have to maintain is around 100 to 1000 standard cubic centimeter per minute, okay, defined at 0 degree centigrade in 1 atmospheric pressure. So these are the typical things that this particular low pressure CVD system which is having. Okay. The gases or the reactant products that will be available within the chamber will be pumped out from this particular site. So this way we have this device, this particular chamber, and then we have to perform the deposition of our different layers. You can see that this hot wall reduced pressure CVD reactors is generally used for deposition of polysilicon, SiO2, and this silicon nitride, okay, stoichiometric silicon nitride. So these three things we can deposit by using this hot wall reduced pressure CVD reactors. Here, one more thing, that it can hold up to 150 mm diameter wafers, and the process, it can process 50 to 200 wafers. Okay. So there are certain advantages of this system, that it is having the excellent uniformity of the thickness of the deposited film. Okay. So it is uniform thickness that we are going to get. But the problem with this type of system is the low temperature, it is the deposition rate will be small. Okay, generally we get the low deposition rate, and we have to use the gases that will be generally toxic and corrosive in nature. Okay, it will be flammable also. So these are the few disadvantages of this particular system. Here you can see we have another system which is continuous feed atmospheric pressure reactor. Okay, it is a APCVD technique. So as I said, that generally APCVD is suffering from the non-uniformity of the thickness of your layer deposited. So here you can see this. What is the mechanism? Okay, the mechanism is we generally having a particular load stack. where we have our wafers. So these wafers will be actually loaded onto this particular conveyor belt. Okay. And then this conveyor belt will keep on rotating, and this will be placed onto this particular heater within this chamber. Okay. And then it will be heated. Okay. And this heating will be done by the convection mechanism. Okay. It will be heated by the convection mechanism, and then the gas will be coming from this central top side. Okay. This gas shower head. So we have this gas shower head, and from this shower head, the gas will enter. Okay. It will be coming to this particular vapors, and then it will be making the reaction, and then a layer will be deposited. So once this operation is over, this conveyor means it will take out this particular wafer, and then it will be unloaded. Okay, it will be unloaded at this particular place. So this way, this will happen. And you remember that while showering the actual gas content that will be used for deposition of the particular layer, you remember that here we have to use the very high gas flow of nitrogen. Okay, as a curtain. It will be used as a curtain. Okay, so at both the sides it will be used as a curtain, so that these gases will not go outside. Okay, it will be only confined within this region. Okay, within this wafer region. Okay, and this way we can continuously load the wafers onto the conveyor belt, and we can continuously do the our deposition process. Okay, and the other side the wafer will be unloaded. Okay, here we have to keep on cleaning this conveyor belt. Okay, so that the contamination should be reduced. All the byproducts gases will be taken out from this side. Okay, this side. And this mechanism generally used for deposition of the SiO2. Okay, SiO2 layer can be deposited by having this. The advantage of this system is that we can have very high throughput. Okay, it will be able to handle the large wafers also, good uniformity. Generally, this continuous feed atmospheric pressure reactor, within this reactor, we can get the good uniformity. But you remember that in other AP-CVD techniques, we generally get this uniformity. Okay, so in this continuous feed atmospheric pressure reactor, we get this uniformity. Okay, but non-uniformity will be available in other AP-CVD, the conventional AP-CVD system. Okay, here the disadvantage is that the fast gas flow is required and need to clean the reactor frequently. Okay. Here you can see we have the plasma enhanced CVD reactor. Okay, so in the plasma enhanced CVD reactor, here we have the cold wall parallel plate reactor. So generally it is made up of aluminum. Okay, aluminum platforms or aluminum electrodes, you can see. This will be the grounded electrodes, and we have another aluminum electrode over here, and then the wafer. On the one side, we have to send the gas, and then a particular electric potential will be applied across these two electrodes. That is going to be generating the particular plasma glow. Okay, the particular glow will be there inside this particular gas, which is going to enhance the temperature within this particular means even at the low temperature, what happens because of this glow. Okay, this reactant gases is going to become active. Okay, whatever the reactant gases we are sending inside this particular chamber, it will become very active due to the glow, and then it will be starts doing the reactions. Okay, it will be starts making the reaction, and the layer is going to be deposited onto this particular wafer. So we have this two system, two different means it is same arrangements. Okay, it is like in a different box it is given a different way, but it is the same system. Okay, so generally this cold wall parallel plate reactors are not used because it is having the limited capacity. It cannot hold very large number of wafers. Okay, and also it cannot accommodate large size of the wafers. Okay, it cannot accommodate large size of the wafers. Generally, this hot wall parallel plate reactors we used, okay, it is similar to your APCVD, a simple APCVD mechanism, but here we have to use the plasma, okay, because we are having the plasma enhanced CVD, okay. So basically, we have to create a plasma, okay. But here, this system is having, means it is having a very large capacity. It can hold large number of wafers, as well as it can also accommodate the big size of the wafers. Okay. So generally, commercially, we use this hot wall parallel plate reactors. Okay. Remember that in the plasma enhanced CVD reactors, basically used uh, when we require a low temperature operation. Okay. The plasma generally, it is actually due to the glow, the reaction is going to take place. It can even, the reaction can take place at the low temperatures. Okay. So generally, this PE, plasma enhanced CVD reactors are used for the deposition of SiO2 layer, okay, plasma assisted SiO2 layer, or plasma assisted your silicon nitride layers. Okay. In this category, we also have the high density plasma CVD technique, okay, which is generally used for very high quality deposition of the layers. Okay. So these are the different systems that we generally use for deposition of the different layers. Okay. Either polysilicon, it may be SiO2, it may be silicon nitride. Okay. So now you can see how this polysilicon can be deposited. Okay. If you remember, I said that this hot wall reduced pressure LPCVD technique, actually chamber can be used. Okay. This particular reactor can be used for deposition of the polysilicon. Okay. So how it is deposited? So basically, it is the pyrolysis of your silane. Okay. Silane gas we generally take, and pyrolyzing means it is thermally decomposing this silane. Okay. That is a thermal decomposition of your silane. Okay. Gas at this particular temperature, 575 to 650 degrees centigrade, in a low pressure reactor. Okay. So if you decompose it at this particular temperature, okay, at low pressure, generally it will be decomposing and it will be liberating this hydrogen gas. And in that case, this silicon layer is going to deposit it, which is your nothing but your polysilicon. Okay. So here we have the two variants. Okay. This variant is, so the one is in which we can use the 100% silane. Okay. And the other one is in which we can use the diluted silane. Okay. 20 to 30% diluted silane in nitrogen. Okay. Generally we use the nitrogen. In both the processes, you can find that the deposition polysilicon means we can deposit the polysilicon on 10 to 200 wafers, and per run, and the thickness uniformity is around plus minus 5%. So this is the typical uniformity that we are going to get. Okay. The deposition rate is typically 10 to 20 nanometer per minute. You remember one thing that we are depositing the polysilicon. Okay. This LPCVD technique or a sputtering technique, both can be used for the deposition of the your polysilicon layer. Okay, you remember that. Okay, LPCVD, low pressure CVD, or a sputtering technique can also be used. Here I'm not discussing about the sputtering, but sputtering can also be used for the deposition of the polysilicon, but normally LPCVD technique is preferred. Okay, so why it is preferred? Because it is giving the better step coverage. Okay. So what does it mean by the step coverage? That I will be explaining you in the subsequent slide, so don't bother about it. So I will be explaining what is the step coverage. So you remember that generally LPCVD is having better step coverage as compared to the sputtering technique, and therefore we generally use the LPCVD. Okay. One more thing is that we can also use the some silicon chlorides. Okay. But generally we use the silane gas. The reason is that this silane is actually having a better coverage over the amorphous material. Okay, so let us suppose that if we have the SiO2 layer, so if we want to grow uniformly over the SiO2 layer, this silane gas is generally having the good coverage. Okay, so that's why we are using this silane. One more point that you have to remember about means if you want to dilute the silane gas, okay, you can also use the hydrogen, okay, other than the nitrogen, we can also use the hydrogen. But generally, why this hydrogen gas is not used as a diluent or a carrier? Because it reduces the deposition rate. It is found practically that if you use the hydrogen, the deposition rate will be very small, and therefore we don't use the hydrogen gas. Now to deposit any layer, okay, polysilicon, whether it is polysilicon, SiO2 or any other layer, there are certain deposition variables, okay. So what are those deposition variables that we need to understand is, you know, that this deposition variables is nothing but your ambient conditions, right? So basically the deposition variables are your temperature, pressure, silane concentration or dopant concentration if you want to get the doped polysilicon, okay, or doped any layer, okay. So that time this dopant concentration also matters, okay? So these are the typical things like temperature, pressure, silane concentrations, okay. So you know that whenever we increase the temperature, normally it is found the deposition rate will increase, okay. With increase in the temperature, generally the rate of deposition increases. When we pressure, we have the pressure, the dependence of the deposition rate onto the pressure will depending on how we actually varies the pressure, okay. So there are three different ways of changing the pressure within the chamber, okay, by changing the pump speed, by changing the nitrogen flow, okay, means by enhancing the nitrogen flow, or by changing the total gas flow, okay, because we are saying that we are sending the nitrogen gas along with the silane gas along with the nitrogen. So we can also change the total gas by keeping the constant ratio, okay, means the nitrogen, amount of nitrogen and amount of silane gas will be constant, but the total amount of gas will be changed, okay. So that is at constant ratio and pump speed, okay. So these are the three different ways by which we can actually increase the pressure, okay. So here you can see that if we increase the pressure, that time generally what happens, a slight increase in the deposition rate in the first two cases is observed. But in the third case, generally the rate of increase in the deposition rate is a little bit faster, okay. It is linearly increases and it is a little bit faster than the other two cases, okay. So generally with the pressures, our deposition rate is also going to increase. And normally, if we talk about the silane concentration, if we increase the silane concentration, okay, this deposition is deposition rate is non-linear, okay. It is not means it is not varying linearly, okay. It is not varying linearly. Basically, when we have the reaction here, you can see this graph also, okay, the effect of silane concentration on the deposition rate. So basically we have the, if we increase the concentration of the silane partial pressure is going to increase, okay. So here we can see that this silane partial pressure, increase in the silane partial pressure is reflecting the silicon concentration, okay. It is increasing the partial pressure, means it is increasing the silicon concentration. And here you can see it is non-linearly, it is changing, okay. It is changing, okay. After a certain amount of time, this increase is very small, but it is increasing very slowly, okay. So it is increasing very slowly. Here you can see in all the cases this is changing, okay. And at different temperatures, this deposition rate is also changing, okay. Temperatures, okay. So here you can see that at 628 degrees centigrade, the deposition rate was very small as compared to 698 degrees centigrade, okay. Here the deposition rate is very large. So basically what happens when we pass or when we send this silane gas, generally this gas is first absorbed onto the surface, and then it will be decomposed into this two form, okay. SiH2 in the adsorbed form and the H2 gas in the adsorbed form. And later on, this adsorbed SiH2 is going to deposit the silicon layer, and it will be having this hydrogen gas in the adsorbed form, and later on this hydrogen gas will be liberated, okay, in the gaseous form, okay. So this having a different reaction time. Okay, all these steps are taking a different reaction of time, and therefore generally it is not a linear function of your concentration. Okay. If suppose if you want to add any dopant, okay, to vary the conductivity of your polysilicon, so normally either we add this particular dopant boron by using the diboron. Okay, so you can add the diboron so that boron can be incorporated into the polysilicon. So this will be our source. Diboron will be the source. So if you add this diboron, okay, that time you will find there will be a rapid increase in the deposition rate. Okay, if you're adding this diboron. Okay, so deposition rate of the polysilicon, you will find it is very much large. It is increasing by a very large amount. Okay. Similarly, if you add phosphine or arsine, you will find that to add these impurities, okay, phosphorus and arsenic, then there will be a rapid decrease in the deposition rate you can observe. Okay. I have not included those pictures, okay, but you can understand from these things, okay, at what time it is increasing and at what time it is decreasing. Fine. Okay, so now we have the deposition of our silicon dioxide. Okay, silicon dioxide. So silicon dioxide, as I said, it can be deposited onto means using the APCVD or LPCVD reactors. Okay, both the reactors can be used. Fine. So basically, here you can see this deposition of the silicon dioxide is having the different temperatures. Okay, so let us say we talk about the low temperature deposition. Okay. Then this low temperature deposition can be done by sending the silane gas with the oxygen. Okay, so if we send this silane gas with the oxygen, then SiO2 layer is going to grow and this hydrogen is going to be liberated. Okay, if you also wish to dope this SiO2 layer with the phosphorus, okay, then you also have to send this gas, okay, for means this particular phosphine gas. And thereby this particular thing is going to be deposited or going to be dope this particular SiO2 layer. Okay. So normally what happens if you use any of the reactor, okay, APCVD or LPCVD, normally you remember, because this is a very low temperature process, 300 to 500 degrees centigrade. This is one of the advantage that because a very low temperature operation, okay, this SiO2 layer, if you want to grow over the aluminum, okay, aluminum metallization, then it is possible. Okay, because I initially explained you that aluminum is having its melting point around 700 degrees centigrade, and therefore because it is deposited at very low temperature, so that time it is possible that we can grow the SiO2 layer over the aluminum also. So these films provide passivation coating over the final device and insulation between the aluminum layers. Okay. Here again, the disadvantage about this is it is having poor step coverage. Okay. So now try to understand that what is the step coverage. Okay. So let us suppose we have initially we had this type of a structure onto the surface. Okay. Just consider this bottom line. Okay. Just bottom line. You don't consider this, because this is our deposited film of SiO2. Okay. So let us suppose initially we had this type of shape onto the wafer surface. Okay. And we want to grow the SiO2 layer onto this particular structure. Okay. So what we need is this thickness of this SiO2 layer should be means uniformly deposited. Okay, the meaning is that you can see we have this horizontal surface, okay, and we have this vertical surface. Okay, so this thickness and this thickness should be same. Okay, this thickness and this thickness should be same. Okay, it should not be like the thickness are different. Okay, everywhere this thickness should be same. So if it is having this type of thickness, it is uniformly grown, whether it is a vertical wall or this horizontal surface. Okay, all over the places, the thickness of the deposited SiO2 layer are same. Okay, it is uniformly means deposited. If this is the case, it is called as the conformal step coverage, okay, which is a very good step coverage, we can say, okay. Conformal step coverage, or we can say it is having a very good step coverage, okay. But because it is having the poor step coverage, the meaning is it is a non-conformal step coverage. So what does it mean? You can see that in sometimes what happens, if we grow this SiO2, means deposit this SiO2 layer onto this type of a structure, we'll find that here the thickness is different, and here you can find that this thickness is different, okay. As we go from top to down, here you can find that this thickness is actually changing, okay, even at these locations, okay, at these particular edges, okay. Here you can see that we have a different type of shape. So this is what we said as the non-conformal step coverage, okay. So generally this type of layer which is deposited is having the poor step coverage. So this is what we are saying, that generally this type of layer is means this type of low temperature operation is giving us the poor step coverage, okay. It is suffering from this poor step coverage. We generally want this type of layers, okay. We don't require this type of layer, okay. Now we have the intermediate temperature deposition. So here you can see this temperature is around 500 to 800 degrees centigrade, and this time we use the tetraethyl orthosilicate, okay, which is abbreviated as TEOS, okay. So it is used in the low pressure CVD reactor. So generally this is the chemical formula of your TEOS, and then after having the decomposition of this TEOS, we are going to get the SiO2 layer, and there will be a certain byproducts, okay. So this byproduct will be removed. So it is basically a complex mixture of the organic and organosilicon compounds. So here you can see this temperature is now ranging from 500 to 800 degrees centigrade, okay. So basically, if the temperature is normally, if it is more than 600 degrees centigrade, okay, your aluminum stability is going to be affected, okay. You remember that, okay. So aluminum will start melting, and therefore this intermediate temperature deposition of SiO2 is not possible onto the aluminum layers, okay. If we have aluminum layers already deposited, then we cannot deposit it over the aluminum SiO2 layer by following this particular intermediate temperature deposition process, okay. So this process has excellent uniformity, conformal step coverage, and good film properties, okay. One more thing, that it can be deposited over the polysilicon, you remember, because aluminum is having less melting point, but polysilicon is having melting point which is around 1400 degrees centigrade, and therefore it can be deposited over the polysilicon gate. The problem with this is high temperature. Obviously, it is a high temperature process, and in this case, we need to use the liquid source. Okay, we have to use the liquid source. The next one is our high temperature deposition. Okay, at this case, we have to use 900 degrees centigrade temperature. Okay, and that time we have to use the dichlorosilane. Okay, with the nitrous oxide. So after having this reaction with the dichlorosilane, this SiO2 layer is going to be formed, and as a byproduct, there will be an HCl gas. Okay, so normally this is also going to give the excellent uniformity. Okay. Over the obviously polysilicon layer, okay. But the problem with this is because of this HCl, presence of the HCl gas, if a very small amount of HCl is also trapped within the SiO2, then this chlorine, okay, this chlorine, a very small amount of chlorine in the oxide, actually going to react with the polysilicon, okay. It is going to react with the polysilicon that causes the film crackings, okay. So therefore, this is one of the disadvantages of this particular thing, because we are going to grow the SiO2 layer over the polysilicon, and if the chlorines are trapped inside the SiO2, this is going to crack the polysilicon film layers. Okay, this is one of the disadvantages. Okay, so these are the things about the deposition of the silicon dioxide. Okay, remember that whatever the deposition variables we have used in the previous slide, okay, Almost the same thing you can also observe. The reaction rate is generally increasing with the temperature, okay, with the pressure, okay. So the same type of observations you can also make for this deposition of the silicon dioxide, okay. And now to deposit the silicon nitride, as I said that first of all, we can have this stoichiometric silicon nitride Si3N4. Okay, so in this case, the first case we can use the atmospheric pressure CVD, okay, at temperature between 700 to 900 degrees centigrade. We have to use the silane and ammonia, okay. These two gases should be used, and after the reaction, we are going to get this particular Si3N4 layer, okay, at this particular temperature. Similarly, it can also be deposited by reacting the dichlorosilane and ammonia, okay, at reduced pressure and the temperature between 700 degrees centigrade to 800 degrees centigrade. So this is the reaction, okay, and then we are going to deposit this Si3N4. So this is this second one is generally having an advantage over this first one, is that it is having the good uniformity, and it is also having the high wafer throughput. Okay, so the deposition will be very fast. Okay, we can deposit this layer very fast. The last one is our the plasma deposited silicon nitride. Okay, so normally in the plasma deposited silicon nitride, what we do is we have to create a argon plasma. Okay, and because of the glow discharge, this particular gas molecules, okay, is going to become active. Okay, due to this glow discharge, it is going to become active, and then it will start making the reaction. Okay, so even at the low temperature, means from 300 degrees centigrade to 350 degrees centigrade, due to this glow discharge, okay, inside the gases, due to the gases means the available gases, like means the argon that we have to use, okay, as the plasma source. So we have to use the argon plasma. So argon gas will be available, and then we have to apply a particular potential onto the electrodes, and that is going to create the plasma. So because of this plasma and the glow discharge within the plasma, within the low temperature even, okay, due to low temperature even also, due to this glow discharge, okay, we are going to having these reactions. Okay, so after having these reactions, we are going to form this SiH4 and 4NH3 will react, and it is going to give you this product SiNH. Okay, so this way we are going to deposit our silicon nitride. Okay, this way we are going to deposit this one. And you remember that because it is the low temperature process as compared to your previous one, okay, this stoichiometric silicon nitride requires 700 to 900 degrees centigrade. So generally this layer is normally not used for, you remember, it cannot be grown over the aluminums. Okay, it can be grown over the polysilicon, but it cannot be grown over the aluminum. Here you can remember, because it is a low temperature operation. Okay, this can be used for deposition of SiN layer over the final metallization. Okay, so generally plasma deposited silicon nitride is used at the final passivation layer. Okay, so hopefully you must have understood something from this lecture. So thank you for watching this video. Stay connected with the channel. I will be coming up with more lectures. Thank you for watching this video.